Hello everyone, this is my homework 7 number 1 about closed loop control system. My name is Nugroho Putri Wicaksono. A block diagram about a closed loop control system. It can be illustrated within this figure like a PID diagram. And this is the set point, or we can call it as RT, R of T. And this is the summation point. And this one is the after we sum the set RT, R of T and the PV process variable, and then we can get error value, and the error value will be fed onto the PID controller. And after the PID, from the P term, proportional term, integral term, and derivative term, we can sum it, and then we can get UT, and then be feed it onto the process variable, and then it will be sent back to the summation point, the first summation point. This is the PID closed loop response. This is the rule when we want to tune PID. This is the examples PID on linear and rotational planes. This is the on the linear plane. I already explained about mass spring damper system, MSD system. Okay. In the previous video, I already mentioned that there is 3 elements: mass, spring, and damper. And M is for mass, F is for applied in the mass spring damper system, and A is acceleration. And when A is configured in the X display of displacement, it will be X double dot. And for the velocity V, this one in the damper's element, it will, if we use it in the X term, it will be X dot. This is free body diagram. From this we can get the transfer function, and from the transfer function we apply the Laplace transform, and from the Laplace transform we can get the open loop transfer system of the system. And we need to apply the PID, and this is the experiment. This is the first trial, the result of the first trial. This is the second trial, and this one the third trial and fourth trial. And then this is the summary. For me, this the fourth trial is give the best value because it already employ a proportional gain, integral gain, and the derivative gain. So the result is quite amusing. The rise time is only 0. Almost 2 second. It's not the problem because the settling time, even though the settling time is, the fourth one is slower than the 2, but the overshoot is only 3 compared to this one. Okay, another example about linear and rotational motion. This is like a position table. We can use a motor servo and servo driver. Usually people assume that there is only one types of encoder, which is rotational encoder or rotary encoder. For me, up until now, I only know this one. And so, for the rotational and linear closed loop control, using this one, we can use two example in one picture, like that. For the rotational closed loop control, we can use the feedback from the rotary encoder. And for the linear closed loop control, we can get the feedback from the linear encoder. Okay. When we use the load encoder or linear encoder for the system, this is the system of how to move the load from the position to the other position, like that. And we can control the location of this one to verify with the pulse that already given to the servo motor, and then we verify the position of the load. So this is the load encoder. This one is used for the motor encoder and the load encoder. It used as a feedback on the closed loop system. This is the cable from the load feedback and this is the motor feedback cable. So there is two in one plan. There is two feedbacks, and we can use the first feedback is used for motor and this one from the linear movement. Even though there is no motor in here, but we can use this one as the feedback. This is the linear and rotary encoder. This is the linear encoder. This is the circuit and this is the one. And this is the magnetic stripes in the linear encoder. Okay, that's all that I can give about closed loop control system and example about the linear and rotational. Thank you so much for your kind attention and see you in the next video.